Hello. So in this part we will discuss about the steady flow of ideal fluids. So as we know that the flow dynamics of an ideal fluid must become much simpler if we assume that the flow is not explicitly depending on time. Okay. So that means that the flow does not have any del T type of thing. So whenever we see some del T of something, that we will say that is zero. So for steady flows, of course, that is same for, that is the same thing for the velocity vector. So del T of velocity is zero. Simply, we can also say that was a trivial thing, but we can also say that del rho del T is also zero. Okay. So here we just say that just for as a corollary that the continuity equation basically can be written like this: 0, this is 0, so divergence of rho v is 0. So remember that in case of incompressible fluids we had divergence of v is 0, but here rho is just independent of time, so there is no explicit time dependence, but rho is a function of space. So here this is divergence of rho v is equal to 0. That is the property of a stationary flow. Okay, although it may look very similar, but this is subtly different. Okay, now what about the case of the momentum evolution equation for steady flows? So you will see that similar to density, we can say del T of v is equal to 0. Okay, and therefore the first term of the momentum evolution equation goes away, and we simply have this gradient of v square by 2 minus v cross omega is equal to minus gradient of p by rho minus gradient of phi. Now this is a new way of writing the force density, body force density G. Okay, so since this is, as I said that this is a conservative force field usually, so that means G can be derived from a scalar potential, let's say phi. Okay. Now let us introduce a very important concept, that is the concept of streamline. Now the concept of streamline is not a concept which is specially defined for incompressible or ideal fluid, but this is a general concept of a flow. It simply says that streamline is defined as such a curve that at every point of that curve velocity is tangential to it. So let's say this is a streamline curve, the purple one. Okay, so at every point, if we just measure the velocity vector at that point, the Eulerian velocity vector, the velocity field, okay, then we will see that the velocity vector is exactly tangential to this curve. Okay, so to this streamline curve. So what is the meaning of that? The meaning is that this is exactly the same direction as the infinitesimal length elements on this curve. Okay, once again, so if you take any infinitesimal length element dl on this curve, then that dl vector and the velocity at that point will have the same direction, and that's why the streamlines definition can be given by this: dl cross v is equal to 0. Okay, now you know the concept of fluid particle, so you can easily understand basically a streamline is nothing but the trajectory of a fluid particle. Okay. Now as this part is simply 0, So if we say for a steady flow, this is 0. So this part is this is equal to this. So just taking these two terms on the other side, we can simply write this gradient of v square by 2 minus v cross omega, okay, plus gradient of p by rho plus gradient of phi. This is 0. So this is the same thing by saying, so this is identically 0, okay. So this part, which is when it is contracted with some length element dl and integrated, okay, over that length element, then this is just equal to 0. And we don't, I mean, this dl don't need to be an elementary length element over a streamline. That can be the length element over any trajectory or over any curve. Now if dl is along a streamline, then what happens? Then this dl dot v cross omega actually should vanish, because you know that if we have this type of scalar triple product, then dl can that can be permuted, and d that will be equal to dl cross v dot omega, and this is 0, so this vanishes. So then if we are just studying along the streamlines, then the lamp vector contribution would vanish, okay, and we simply have integration dl dot gradient of v square by 2 plus gradient of p by rho plus gradient of phi is equal to 0. Now we integrate. If we integrate, we will see that dl dot gradient of v square by 2 is nothing but d of v square by 2, the differential of v square by 2, right? So integration, okay, over so when it is integrated over some trajectory, okay, over the streamline, okay, over a streamline, then it will simply be just giving you v square by 2, okay, and that one, when it is integrated, so again the gradient of p dot dl, so once again gradient of p dot dl is nothing but dp, okay. So integration over this by rho is nothing but integration of dp by rho, and that's exactly what I have written over here, okay. And finally integration over dl dot gradient of phi, in the same way this will be simply integration over d phi, and that is phi. Now in this part on the right hand side you are integrating basically, so that is, I mean, I have written 0, but this is not a, I mean, this is not the correct way of writing, so that should be some 0 which is integrated over dl. So that will finally give us some so yeah, so this is, I mean, if we integrate, so basically this is 0, that is true, but once again this is 0 when this is integrated over this is actually this, okay, yeah. So this will give us some constant of integration, and this is nothing but the so-called Bernoulli theorem, okay. That is the sum of these three things, v square by 2 plus dp by rho integration plus phi is equal to constant, okay. So in a sense this corresponds to the density, massive density of kinetic energy. This corresponds to the so-called, I mean, potential energy due to the internal forces, and this corresponds to the potential energy due to external body force, okay. So for an incompressible fluid, actually we have a simpler case, and rho is constant, so rho can be taken out of the integration, okay, and it will simply be then integration dp, 1 by rho integration dp, which will be simply p by rho, and we have this simpler form, okay. So this type of thing, why I am discussing all these things, this will be very much interesting and important when we will discuss different type of fluid surface instabilities in astrophysics. For example, Rayleigh-Taylor instability, Kelvin-Helmholtz instability. So in order to derive a general treatment or a general formulation for those type of instabilities or stabilities in case of like helioseismology, okay, that we will discuss, or stellar oscillations, we will see that this type of properties are needed there. Okay. So another thing, so that was one thing to discuss. So Bernoulli theorem or Bernoulli principle in case of ideal and stationary fluids. So of course you see that I mean here in this case we are actually like mixing two concepts. So one is streamline, and streamline has a very general streamline is very much general. So streamline is not very much specific about ideal fluid or anything. So whenever there is a flow we have streamline, but then we have merged this streamline to steady flow of ideal fluids. Okay, that is something to remember every time. Okay. In this part, we also define or also discuss another important property or another important concept, that is stream function. Just now, just some minutes ago, sorry for this. Yeah, so just a moment ago I said that streamlines, they are very much general. Whenever there is a flow, so the trajectory of the fluid particles, they constitute the streamlines. Stream function on the other hand has a very specific domain of application. So that I am coming. Okay. So first let us start by saying that in many cases of astrophysical fluids, the flow is practically two-dimensional. Okay. So this type of thing can happen, for example, when a cyclone is forming. Okay. Let's say when a cyclone type thing is forming, let's say when we are talking about the dynamics of a disk type of thing, for example, a galactic disk or something. So the flow is actually very much nearly closely two-dimensional. Okay. Then this type of concept of stream function can be of utter importance. So if the flow is incompressible, then we can actually say that divergence of V is 0, that we already showed. And if the flow is incompressible, then we can write the velocity, okay, to be derived from a vector potential. So that we all know from our knowledge of preliminary vector calculus that whenever a vector field has a zero curl, then the vector field can be derived from a scalar potential, and whenever a vector field has a zero divergence, this can be derived from a vector potential. Okay, so a very popular example is of course the for magnetic field, which is by virtue of the absence of the monopoles has zero divergence of B is 0, and that's why we know that there is a vector potential of a magnetic field. So in case of velocity, this is not always true. Only when the velocity is only when the velocity corresponds to the velocity of an incompressible fluid, then only the divergence of the velocity is equal to 0, and then we talk about a vector potential of a velocity, okay, which we simply call here as AV. Okay, so velocity will be curl of AV. For 2D problem without Z dependence, this curl of this AV or the velocity vector potential can be written as minus of a scalar function psi, which is a function of x and y only, times the unit vector in the z direction. Okay, z direction simply means the direction which is perpendicular to the plane of the problem. So if this is the plane of the problem, so then this is the z direction. Okay. So whenever the vector potential can be written in this form, and that is only possible in 2D case, then this scalar function is called a stream function. So stream function is not a general concept. First of all, your flow has to be incompressible. Then your flow has to be practically of 2-dimensional. Then only you can talk of a stream function. Okay. So streamline is general, stream function is not that general. The minus sign is chosen only by convention. You can just say it is plus psi. That is also possible. Okay. Now if I just take this is as a definition of 2D vector potential, okay, for the velocity field of an incompressible fluid, of course, then V is equal to minus curl of this whole thing psi times Ez cap. Okay, and then you simply know that what will be Vx. So Vx will be the x component of this product, and that will be simply minus del psi del y. Okay. Similarly, what will be Vy? Again, if you calculate this, please calculate that. Small calculations are always encouraged to do at home. Here in the lecture, it is not possible to show every single step of calculations. So I will hope that you will try this at home. So Vy will be plus del psi del x. Okay. Now we know that streamlines are defined as V cross dr is equal to 0 or dl. I mean just dr or dl, whatever, that is not a big deal. Okay, 0. Where dr or dl, they are the incremental incremental length elements, length vectors or length elements of a streamline. Okay. If we can write that, then basically from this definition we can write that the streamlines can also be written like this. Just I am doing this cross product and I am writing this, because dr or dl is nothing but dx I cap plus dy j cap. Okay, because we are in 2D, then we are just doing the cross product, and we have Vy dx minus Vx dy is equal to 0, and Vy is nothing but del psi del x. So, and Vx is nothing but minus del psi del y. Okay, so finally that was minus Vx, so it will be plus del psi del y. So the whole thing will be then the what is then this cross product? This cross product will now simply be del psi del x dx plus del psi del y dy, and that is equal to 0. And what is this? Basically this is nothing but the total differentiation of the function psi, d psi, and that simply says that along a streamline d psi is equal to 0. So how to characterize in a very efficient way a stream function? So stream function is something which is constant. Okay, so which is the vector potential, which gives you the magnitude of the vector potential in a 2D incompressible fluid flow, and which is conserved or which is kept constant along a streamline. Okay. So in this part we have learned basically two concepts. One is of the steady flow, okay, where we introduce the concept of streamline, and then we also learned the concept of stream functions. Okay, now just for your interest, just what you can do as a very good exercise at home, that velocity fields, when they are irrotational in nature, then you can actually also define for the velocity field a scalar potential. Okay, now let's say you can assume an incompressible fluid which is also uh, irrotational. Then can you say something about some properties of the velocity and its corresponding potentials? Can you do that? So it's at the same times incompressible and irrotational. Okay, so you think about that. Okay, so that is something to think about. And I mean, whether this is totally an impossible case or it has some mathematical significance, just think. Okay, and in some during the forum discussions, if you still have some confusion or if you come out with an answer, you can tell me and I will try to make some discussion on that. Okay, thank you.